All right, today we're going to talk about vectors, and you really already know most of what we're going to talk about today, either from just learning about vectors in previous classes or mainly from the parametric equations that we've talked about in calculus already. So the definition of a vector is that it's a directed line segment, and it's made up of two components, both the magnitude, which is you can think of as the size or the length of the vector, and then the direction or the angle of the vector. So a vector in standard position has its initial point at the origin. So if you have the vector x comma y, then the initial point is at the origin and the terminal point or the ending point is at the point x comma y. And the magnitude of the vector or the length is the square root of x squared plus y squared. And that makes complete sense if you draw a triangle. Then the horizontal piece of that triangle would be length x, and the height of that triangle would be y, so you've created a right triangle, and the Pythagorean theorem would give you that the hypotenuse, or the length of that vector, is the square root of x squared plus y squared. And in terms of a vector, the magnitude is denoted with absolute value, so it doesn't really mean the same thing in the traditional sense of absolute value that you're used to. It just means the magnitude or the length, and you're supposed to use that formula right there. And then the direction of the vector is the angle from the positive x-axis. So that angle right there, and you can find that by taking the tan inverse of y over x. And that's just kind of vector basics. We're going to move beyond that, and really for our purposes, the main thing we're going to use vectors for is really just to describe parametric equations, or just a way to write a set of parametric equations. So if you consider the parametric equations, x equals x of t and y equals y of t, then a function of the form r of t equals x of t comma y of t is called a vector valued function. And then it just goes on to say that the component functions x and y are real valued functions, so real numbers, and the parameter is t, or the independent variable is t. And if x and y are twice differentiable functions of t, meaning you're able to take the derivatives of both x and y 2 times, and r is a vector valued function given by r of t equals x of t comma y of t, then the velocity of the function would be given by the velocity equals r prime of t, and literally that just equals x prime comma y prime. You literally just take the derivative of x and the derivative of y. And the acceleration is the same way. The acceleration is going to be the second derivative of the position function, and that's going to equal x double prime comma y double prime. You literally just take the derivatives of x and the derivatives of y. And then speed is the magnitude of velocity. So speed would be the square root of x prime of t squared plus y prime of t squared. All right, so let's put this to use. Find the velocity vector, the speed, and acceleration vector of a particle that moves along the plane curve described by r of t equals 2 sine 5t comma cosine t over 2. All right, I'm going to go through the rest of these problems pretty quickly, so feel free to pause the video if you need to catch up. So we're given the position vector, and if we want to find the velocity vector, then v of t is literally going to equal r prime of t, and we get that by taking the derivative of the x part and the derivative of the y part. So to take the derivative of 2 sine 5t, we're going to have to use the chain rule. So the derivative of sine is cosine, so it will be 2 cosine 5t times 5, because you have to take the derivative of the argument. So that will give us 10 cosine 5t. All right, and then for cosine t over 2, it may be easier to think of that as cosine 1/2 t. And the derivative of cosine is negative sine times the derivative of 1/2 t, so negative 1/2 sine 1/2 t. And there is our velocity. So then acceleration is just going to equal the derivative of velocity. So again, using the chain rule, the derivative of cosine is negative sine, and I'm going to have to multiply by the 5 because that's the derivative of the argument. So I'll get negative 50 sine 5t, and derivative of sine is cosine half t, but I have to multiply by the 1/2 of the argument, so that gives me negative 1/4 cosine half t. All right, and then speed is the magnitude of velocity, and we have the formula right up there. So that's going to equal the square root of x prime squared, so 10 cosine 5t, quantity squared, plus y prime squared, negative 1/2 sine half t, quantity squared. And that's all there is to it. Okay, let's look at how this is tested on the AP exam. It's very straightforward, and it's the same questions over and over and over again each year. So it's this particular type of question has been very predictable in years past. Okay, so this particular one, we've got a particle moving along a curve in a plane, and that has position x of t comma y of t at time t seconds. So we've just got the position of the particle in terms of parametric equations, and then they're specifically going to give us x dx dt and dy dt. So they're giving us x prime and y prime. So we immediately need to start thinking, okay, they're giving us velocity. And then we're told at time t equals 1, the position of the particle is negative 2 comma 5. All right, part A, write the equation of the line tangent to the particle's path at t equals 1. All right, so we've been writing equations of tangent lines for forever, it seems. So we know that the two things we need to write the equation of a line are a point, and at t equals 1, we were given that the particle is at the point negative 2 comma 5. So we already have that. And then all we need is the slope. Well, for parametric equations, we know that slope is dy dx. Always, slope is always dy dx, no matter what. And in parametric mode, dy dx is dy dt over dx dt. And we are interested in the slope at t equals 1. So the appropriate way to write this would be dy dx at t equals 1 is equal to, and then we can plug our 1 into our dy dt and dx dt. So when I plug 1 into dy dt, I get negative 4. And when you plug 1 into dx dt, we get positive 4. So dy dx is equal to negative 1, or our slope is equal to negative 1. So now we can write the equation of our tangent line, y minus 5 equals negative 1 times x plus 2. And we're done. Please, anytime you need to find slope, please write dy dx is equal to dy dt over dx dt. It's just one of those things that if you think it, you need to write it, and it's what you're thinking, so please write it down on your paper. Okay, part B, write an expression that can be used to find the x coordinate of the particle's position at t equals 4. Do not solve. Okay, so we essentially have the velocity of the particle, and we're trying to find its position at time t equal 4. So this just goes back to that fundamental theorem of calculus, where you take a known position and integrate the velocity between the known time and the time that you're trying to get to. And that's not any different with parametric equations, except that you just have to do the x part and the y part separately. And this particular question is only asking us for the x part. So the x coordinate at time t equal 4 could be denoted as x of 4. And we are going to start with a known position. And we were told up here that at time t equals 1, the particle was at the point negative 2 comma 5. Well, the x value would be negative 2, so that's what I'm going to use for this. And then I need to integrate dx dt, since I'm dealing with the x component, which is t squared minus 7t plus 10, between the time interval of this known position, which occurred at t equals 1, and the known time, which occurred at t equals 1, and the time that I'm trying to get to, which is t equals 4. So I've done what the question's asked right now, is I've just set up an expression that could be used to find x of 4. If it had actually asked us to find x of 4, then of course we would have had to have integrated t squared minus 7t plus 10, plugged in the 4, minus plug in the 1, and then add that to negative 2. Okay, part C. For what values of t, if any, is the particle at rest? All right, well, remember velocity describes the motion of the particle. So if the particle's at rest, it is not moving it's not moving left or right, nor is it moving up and down. So anytime we're looking for where the particle is at rest, we are looking for where dx dt and dy dt equals 0. So they both have to equal 0 in order for there to be no movement of the particle. There can't be any horizontal movement and there can't be any vertical movement. All right, so if we take dx dt and set it equal to 0, then we would, in order to solve that, we would need to factor it. So dx dt factors into t minus 5 times t minus 2. And we would end up that dx dt is equal to 0 at t equals 5 and t equals 2. So at t equals 5 and t equals 2, the particle is not moving left or right. There's no horizontal movement. But we also have to take into account the vertical movement. So we need to set dy dt equal to 0. And in order to solve that, we would need to factor that one. And it will factor into t plus 3 times t minus 2. So we would get t equals negative 3 and t equals 2. So the time when both dx dt and dy dt equals 0 would be at t equals 2. And the explain your answer is that both dx dt and dy dt equals 0. So somewhere on your paper, you have got to physically write both dx dt and dy dt equals 0. All right, for what values of t is the line tangent to the path of the particle vertical? Give a reason for your answer. Okay, a vertical tangent line has an undefined slope, and we know that slope is always dy dx. But in this case, since we're using parametric equations, it's dy dt over dx dt. So the only thing that could make the slope undefined is if dx dt equals 0. But dy dt needs to not equal 0 as well. Because if they both equaled 0, then we would have that indeterminate form that we talked about last chapter. So a vertical tangent line is where dx dt is 0, but dy dt does not equal 0. So I conveniently put this one right after part C. And part C, we set both dx dt and dy dt equal to 0. So if you look back at your work for part C, you will see that dx dt equals 0 at both 5 and 2, but we're looking for where dy dt is not equal to 0. So it would have to be at t equals 5. And your reason for your answer is that dx dt equals 0 but dy dt does not equal 0. All right, part E, describe the motion of the particle at t equals 3. Justify your answer. Okay, again, the velocity of the particle describes the motion of the particle. So we need to find the velocity at t equal 3. So that involves finding x prime of 3 and y prime of 3. And x prime and dx dt are the exact same thing. So you can either say dx dt evaluated at t equals 3, or you can say x prime of 3. Same thing. So if you plug a 3 into x prime, you end up with -2. And if we find y prime of 3, you end up with 6. So because dx dt is negative, that means that the particle is moving to the left. Dx dt describes the horizontal movement. So the particle is moving left because x prime of 3 is less than 0, and up because y prime of 3 is greater than 0. So you take into account both the horizontal and the vertical movement. All right, F, find the speed of the particle at time t equals 3. So we know that we have a speed formula, and speed is the magnitude of velocity. And the magnitude of velocity is the square root of x prime squared plus y prime squared. And if we're looking for the speed at a particular time, then that formula would become, in this case, x prime of 3, the quantity squared, plus y prime of 3, the quantity squared. And again, I very strategically helped you out here and used the same time as the previous example. So we've already found x prime and y prime of 3. So it is the square root of -2 squared plus 6 squared, which would give us 4 plus 36, so the square root of 40. All right, and then the last one is write an expression that represents the total distance the particle traveled for the time between 0 and 4. All right, remember from our discussions about parametric equations that total distance is the same thing as arc length. And arc length is yet another formula that you need to have memorized. So arc length is essentially the integral of speed over the time period. So the time period is 0 to 4, so we're going to have the integral from 0 to 4 of the square root of x prime squared plus y prime squared. So x prime is t squared minus 7t plus 10. And y prime is t squared plus t minus 6. And quantity squared, all underneath the square root. And we're writing an integral, so don't forget your dt. So that is our expression that represents total distance. All right, tomorrow in class we will work some more problems that are similar to this. Have a great day, and I will see you tomorrow.